Hello, everyone, and welcome to another digital design class. In the previous class, we started combinational logic circuits. And in general, we have two types of circuits in logic design. We have combinational circuits and we have sequential circuits. Combinational circuits are the circuits that do not have any feedback, as you remember, therefore they don't have any memory, and the output is only dependent on the input at that time. The previous inputs and the previous outputs do not affect the output at each time. But the sequential logic gate is that for that it's going to be different because that has a feedback and it has a memory. And we learn how to analyze and design combinational logic circuits. We did some examples using the truth table and the K-map on how to solve an example of first we gave a logic circuit, and from that we extracted the truth table, and using the K-map from this truth table we were able to analyze it and determine the Boolean function for it. I also gave you an example, and we solved an example on, for the BCD to excess of 3 converter. Again, using the truth table, we created the K-map, and for each output, we created a K-map. Here, the outputs were W, X, Y, Z, and from that K-map, we were able to determine the Boolean function for each output or each variable. And using these equations, these functions, we can design the circuitry, the digital circuitry for this BCD to excess of 3 converter. Let me start from this. So again, the previous class we learned how to build the K-maps, and we finished at this point by finding W, X, Y, and Z functions. Now we want to build the circuit that represents a BCD to excess of 3 converter using these 4 K-maps. So the first K-map we found W to be A plus BC plus BD. So simply we can have first of all, we have A, B, C, and D. So 4 inputs, and we have BC as an AND gate and BD as an AND gate, and A and BC and BD are all connected to each other using an OR gate. So what I can do, again, I can use each of these, and I just mentioned one of them. So for example, for W, let me bring my pen. So for example, for W, it's going to be A plus B plus C, B times C plus D. In other words, it's A plus BC plus BD. And I can write it like this as well. So you can see the A input is OR, and this is B. And here we have C plus D. So C plus D. So this is going to be B times C plus D, which is equal to BC plus BD. And all of that is OR with the A. So W would be A plus BC plus BD. And we could do the same thing for X, Y, and Z. The easiest one was obviously Z. It's D prime, so we would connect D with a NOT gate to the output C. I'm just going to erase it so you can take a look at it and think on it for a few seconds. Again, we were given a K-map, a truth table, for example, or we're given a K-map. If we're giving a truth table, we would extract the K-map. Sometimes in the questions, we directly provide you with the K-map. And from that K-map or the table, we can determine the Boolean functions for each output. And using those Boolean functions, we can design the circuit for it. As you can see in this circuit, we don't have any feedback. Therefore, this is a combinational logic circuit. Now, let's solve it for another one. And this one is called a 7-segment decoder. You would see 7 segments. You actually see them a lot in different applications. These 7 segments are usually used to show numbers. And one thing that you usually see is in elevators to show the numbers. Usually those are made out of 7 segments. So why do we call them 7 segments? Because it has 1, 2, 3, 4, 5, 6, and 7 LEDs, usually 7 segments. That's the reason we call it 7 segments. And we show them with A, B, C, D, E, F, and G. Okay. Now, for this 7 segment, if I want to show the number 0, for example, if I want to show the number 0, which LEDs should be turned on? A, B, C, D, E, and F are on, and G is turned off. Okay. What if I want to show 3? So if I want to show 3, I would show it like this. Yes. So A, B, C, D are turned off. E and F are turned on and off, and G is turned on. So A, B, C, D, and G are turned on. And it shows. So the numbers that we can show with the BCD, we can actually represent it on a 7 segment as well. So we can show actually any number between 0 and 9 on a BCD. And we can show the same thing on a 7 segment as well. Okay. If we want to show 10, we need 2 of these 7 segments. So we can easily represent it by BCD, a BCD code, which is again between 0 and 9. If I want to show, for example, 8, I have to turn on all the 7 segments, A, B, C, D, E, F, G. What if I want to show number 6, for example? A, C, D, E, F, G gives me numbers. For example, if I want to show number, 6. Or if I want to show number 8. Why did I do that? Or if I want to show number 7, it's going to be A, B, C. So
is 1 going to be BC or FB?
BC. Depends. Sometimes you can show it with both of them, but usually it's BC. Yes. You can also show other characters as well. For example, in a elevator, you may see that we also show characters like P means parking. So that's going to be A, B, F, G, and E. And what else do we usually show? We can also show this as well sometimes. And what is this? G, or ground. Sometimes we can show that as well. Okay. And another thing that I see a lot that we can show is this as well. And what is this? E. And error. You could show error with this, for example. Okay. So you can use the BCD and allocate number 10, 11, 12, 13, 15 to park, which is parking, ground floor, error, something like that, like A. But obviously you can't show B because they will confuse B with 8. But you can also show, for example, A as well. Okay. So 7 segment has its limitations. Obviously, it's good for showing all the numbers. Sometimes in an elevator, you can allocate 1 or 2, like parking, and you can easily program it. And I can show you actually how to do that using Arduino to be able to program it and show, for example, parking or an error or something like that. Now, we can show this and actually express this 7 segment using a BCD code. So we can have a BCD code and given to a converter, and at the output we can have the 7 segments, or A, B, C, D, E, F, and G, this 7 LEDs. Now we can start from 0, 0, 0, 0, which is the number 0. And if I want to show number 0, which ones should I turn on? A, B, sorry. Yeah. I need A, B, C, D, and E. Now, A, B, you can see on the table that A, B, C, D, E, and F, all the LEDs on the border are turned on, and G is turned off. So when it's 1, it means it's turned on. When it's off, it means it's when it's 0, it means it's turned off. Now to show number 1, for example, as you mentioned, B and C would show number 1, and the rest of it would be 0. So this would be 0, 0, 0, 0, 0, and these two are 1. So you can see 0 and then 1, 1, 0, 0, 0, 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after 9, we don't have a BCD code, so we can put don't care. But as I mentioned, if you want to like do programming for the elevator, I don't know why my pen doesn't work on 7, but you can allocate, for example, number 10 to parking, or number 11 to error when you have an error. Or you can show, for example, C means like close the door, something like that. Now, I want to know how I can design this converter to convert a BCD code to a 7 segment, or in other words, to be able to give it some numbers and to be able to display that number on a 7 segment. So to do that, we need to have 7 different K-maps. And we can use the same system that we had before. We can show A, and I'm going to represent just A here, with the 4 variable that we have, which is W, X, Y, Z. And for this particular example, A is equal to 1. At M0, it's equal to 0. At M1, it's equal to 1. At M2, it's equal to 1. At M3, equal to 0 at M4, and then 1, 1, 1, 1, 1. And the rest of it is don't care. So again, this is M0, 1, 2, I'm sorry, 3, 2, 4, 5, 7, and 6. 8, 9, 11, and 10, 12, 13, 15, and 14. And now you can see where we have 1s and 0s, we just replace it in the K-map. Now, if I want to do this for B, this is A. I want you to do this for B, C. We would do it for B now, but I want you to, at home, this is going to be your homework. You're going to do it for C, D, E, F, and G. You have to build all the K-maps for them. Now for A, if we want to do it, we can combine these four together. And then I can combine these four together. And finally, I can combine I want to find a, yeah, that one is going to be left out. So these four together and these two together, or these four together. So different ways that we can. And if I do that, A, or I can do the H and add it down, you're going to get the same results. You're going to have multiple simplified functions, but all of them are correct. And if I do these 8, or I can do the 4 on top right, then and the 4 in the middle, and the 8 in the bottom, and the 4 at the corners. And A would be equal to W plus Y plus XZ plus X prime Z prime. Now, I'm going to do it for B, and for C, D, E, F, and G, I want you to do it at home. So if I want to do it for B, I'm going to draw a K-map again. Again, this is M0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, and 10, 12, 13, 15, and 14. Now, I'm going to fill the map. So for B, we have the second column. We know that from 10 to 15, it's don't care. So I can fill that out. 10, 11, 12, 13, 14, and 15 is don't care. I can replace it with zeros as well. Let's replace it with the don't care. So 10, 11, 12, 13, 14, and 15 are don't cares. M0 is 1. M1 is 1. M2 is 1. M3 is 1. M4 is 1. M5 is 0. M6 is 0. And M7 is 1. M8 is 1. And M9 is 1. Now, if I want to combine them, I can combine these 8 together. I can combine these 8 together as well, the 8 on the bottom and the 8 on the 4 on the top. I can combine these 4, and I can combine these 4. So if I want to combine the 8 in the bottom, by the way, this is W, Z, X, and Y. So if I want to combine the 8 at the bottom, it's going to be equal to W. So F would be equal to W. W, yep. And if I want to combine the 8, the 4 in the bottom with the 4 in the top, it's going to be X prime. So W plus X prime. And these 4 are going to be equal to YZ. And these 4 are going to be equal to Y prime Z prime. So it's going to be W plus X prime plus YZ plus Y prime Z. Now I want you to do it for C, D, E, F, and G at home. Okay. Now, another type of combinational logic circuit. Do you want me to go back, or is it okay? Yeah? Are you doing? You all good? Okay. So another type of combinational logic circuit that we have, which are very important actually, are called the adders. The adders are used to add binary numbers together. We have half adders and full adders. And a half adder adds 1 bit to 1 bit. So it's going to be adding 1 bit plus 1 bit. And it produces a sum and a carry. So for example, if x is equal to 0 and y is going to be equal to 1, 0 plus 1 gives us 0, 1. So the carry is 0 and the sum is 1. But if I have 1 plus 1, then C would be 1 and S would be 0. So the carry is 1 and the sum is 0. So a half adder has 2 inputs and it has 2 outputs. And if I want to write the truth table for it, we would have 4 possible outputs. X, Y is 0, 0. Then the sum and the carry would be 0. If X, Y is 0, 1, the sum would be 1 and the carry would be 0. If X, Y is equal to 1, 0, again, the sum would be 1 and the carry would be 0. And if X, Y is 1, 1, the carry would be 1 and the sum would be 0. A half adder is made out of an XOR and an AND gate. We connect the inputs to the XOR, and the output of the XOR gives us the sum. And if we connect the inputs to an AND gate, it gives us the carry. Now, a full adder is technically a combination of 2 half adders. You add 2 half adders, you combine them, you can create a full adder. The full adder can add 3 numbers together. So it's going to add 1 bit plus 1 bit plus 1 bit. It's going to be x plus y plus z. For example, if x is 1, y is 1, and z is 0, we're going to have 1 plus 1 plus 0 gives us 1, 0. So the carry would be 1 and the sum would be 0. If we add 1 plus 1 plus 1, then the answer would be 1, 1 or 3. So this carry is 1 and the sum is 1. We have 3 inputs. Therefore, we're going to have 2 in the power of 3, 8 possible outcomes. If we want to write the truth table, if x, y, z are 0, 0, 0, the sum would be 0, the carry would be 0. If it's 0, 0, 1, the sum is 1, the carry is 0. If it's 0, 1, 0, the sum is 1, the carry is 0. If it's 0, 1, 1, the sum is 0 and the carry is 1. Again, if we have 1 1s, the sum would be 1, the carry would be 0. If we have 2 1s in the input, the sum would be 0 and the carry would be 1. And if we have 3 1s in the input, the sum would be 1 and the carry would be also 1. If we want to write the K-map to extract the function for a sum and carry, we can use the truth table again. For the sum, it's going to be 1 at M1, M2, M4, and M7. So M1, M2, M4, and M7. And you can see that this table is exactly like the XOR function. And if I want to write the carry table, the carry is 1 at 3, 5, 6, 7. So 3 and 5, 6, 7. If we combine them, C is going to be XY plus XC plus YZ. So using these 2 functions, we can build its logic circuit, and this is going to the logic circuit this is going to look like. This is going to be how it's going to look like. And for the sum, we have 4 AND gates and 1 OR gate. And for the carry, we have 3 AND gates and an OR gate. Now, for the sum, we can replace that simply with a 3-input XOR gate. So an easier way to represent it is by just using a 3-input XOR or 2 XOR gates combined together. That creates our sum, and the carry is 3 AND gates and an OR gate. Another way to build a full adder is to combine 2 half adders together, and we can use 2 half adders and simply connect them together to build a full adder. With the addition of an OR gate, obviously. So, and this is how it's going to look like. This is one of your labs that you're going to do hands-on experience, is to build a half adder and a full adder. A half adder needs 2 gates, an XOR and an AND gate, and a full adder you need 5 gates, 2 XOR, 2 AND gates, and an OR gate. Now let's test the full adder that we built. Imagine if X is 1, Y is 0, and Z is equal to 1. I want you to find the sum and the carry in this. I want to check and see if the design is correct. So X is 1, Y is 0, and Z is 1. I want you to think on it for a few seconds and so for the first XOR gate, if X is 1, Y is 0, XOR of 1, 0 gives us what? 1. Thank you. And the AND gate, this is 1, this is 0, the AND gate would be 0. So the 1 here is also connected to the 1 here. So this 0 goes down to the OR gate. Now what about Z? Z is 1. And the Z is again connected to the upper XOR gate. Okay. So 1 and 1 gives us 0. 1 and 1 AND gives us what? 1. 1 OR with 0. And S would be what? And we know that if we add these two, gives us 1, 0, or 2. Okay. Now let's try it for 1, 1, 1, 1. So imagine if X is 1, Y is 1, and Z is 1. We want to find S and C. So if all the inputs are 1, 1 and 1 XOR would be what? 0. 1 and 1 AND would be 1. Yes. Now the 1 goes down here. I don't care even about the other input because this is an OR gate. I already know that. If one of the inputs of an OR gate is 1, the answer would be what? 1. So I'm going to concentrate on finding the sum. So this is 0, and this is 1. 0 and 1 XOR would be what? 1. And again, we know that, yeah, 0 and 1, this one would be 0. But so if we have, because we have a 1 and in the other inputs of the OR, it's already 1. Now we know that if we add these 3, it's going to give us 1, 1, or 3. Okay, is it clear? I have seen multiple times in FE, the exam, that they had a question, they gave a question on full adder and half adder. One time I remember the question is, they will give like 4 different circuits and ask which one is a half adder. If you memorize it, it's easy. If not, you can just simply use a truth table to solve it and see which one gives the correct answer for a full adder or a half adder. Now, another type of adder that we have is called a binary adder. And usually it's a combination of, if we combine the full adders together, we can create a binary adder. There are specific ICs for binary adders as well. and we have, for example, a 4-bit to 4-bit adder. You can add 4 bits to another 4-bit, and this particular example is a 4-bit adder, and again, you can use multiple full adders together. Here we need 4 full adders to be able to add 4 bits by 4 bits. And the good thing about the full adder, as you remember, full adder has 3 inputs and 2 outputs. And the third input could actually be used to add the carry on from the previous stage to it. So the way that we connect them is we connect the third input of each full adder to the carry of the previous adder. And on the top right, you can see the how we do that. So for example, x0 and y0, and we give it a 0 for the other input, gives us with S1 and C1. And C1 is added to the inputs of the second full adder, and then the carry of the second full adder is added to the third full adder, and so on. So I can build like 100-bit by 100-bit adder by just combining these full adders. I can add 100 full adders together and put them in cascade and add 100 bits to 100 bits. You may have a propagation delay. The problem with this particular system is until I find the result of the first one, I cannot find the result of the second one. It's going to be wrong because I don't know if the carry is 0 or 1. So it's going to propagate the delay. If this one has a delay, or if I have 1 microsecond delay for each of them, it's going to, and I have 4 of them, I'm going to have 4 microsecond delay for all of that. The delay is going to be propagated throughout the system. This is the problem with all the series processing that we have. That's one reason. That's a reason that we have multiple core CPUs, because we want to do them in parallel. We want to sometimes do the process and the calculation in parallel to be able to increase the speed, the processing speed. So we have a carry propagate addition. We have certain ICs which have these full adders already embedded. You don't have to wire them and connect different full adders together. And one example is a binary adder, where you're going to have 8 inputs, 4 input from one number, 4 bits from another number, and you're going to have 5 outputs. And there's C0, which is the initial carry in. You can connect that to the ground. You would usually always give that to 0. But if you want to build an 8-bit by 8-bit adder, you can add 2 of these ICs together and connect C0 to C1 of the first IC. Does it make sense? So here I'm adding 2 4 bits together. But if I add this to another, and this is 4 bits by 4 bits, and I have 4 outputs, and then I could have Y4 to Y7 and X4 to X7. The only thing that I have to do is to give the carry of the first one to the second one. And now I can add 8 bits by 8 bits. If I want to add, I can have 10 of these, then I can add 40 bits by 40 bits. Okay. Now, the carry propagate adder, as I mentioned, we have a problem with the delay. And we can add the carry of the first IC to the second one and expand on that. Instead of having like 10-bit, 4-bit by 4-bit, we can have a 10-bit by 10-bit adder and so on. But the problem that this causes is the propagation delay that we have. And this is a carry propagation example that you can see. When the correct answers are, our outputs are available, the critical path counts the worst case. And for this example, A1, B1, C1 gives you C2, C3, and C4. So the delay again is is until we don't have the answer to A1, B1, we can't find, for example, we can't get to the next digit in A1, A2 and B2 and so on. So when 4 bits full adder, we would have 8 gate levels or n bits, or 2 in the power of n gates. Because adding each number to other number is by itself, it's a half adder, and a half adder is built out of 2 gates, an XOR gate and an AND gate, for example. So you can see that here as well. And by these two, by the way, this creates a full adder. And each of these are a half adder again. So to reduce the propagation, the carry propagation delay, we employ, first thing that we can do is to employ faster gates. We can have a look ahead carry, which is more complex, but it's faster. We have the carry propagate, which PI is equal to AI XOR with BI. We have the carry generate, with GI is equal to AI BI. We have the sum, which is SI equal to PI XOR with CI. We have the carry, which CI plus 1 is equal to GI plus PI CI. C0 is our input carry. C1 is going to be G0 plus P0 C0. C2 would be equal to G1 plus P1 C1, which again, if we want to simplify C1, again, it's equal to G0 plus P0 C0. So I can put it here. And finally, C2 would be G1 plus P1 G0 plus P1 P0 C0. And in the same way, C3 is going to be G2 plus B2 C2. And we already know, again, that C2 is equal to G1 plus P1 C1. And when we replace it, C3 would be equal to G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. So you can see that when you add more numbers, you're going to have a higher number of complexity. This is an example of a carry look ahead adder. The logic diagram, the inputs are P2, G2, P1, G1, P0, G0, and C0. And the outputs gives us C1, C2, and C3. And what this does, it first calculates all the carries and at the same time adds all the numbers. So yeah, at the end, you're going to just have everything. Again, it's, as mentioned, it's a look ahead carry. So it calculates the carries before it adds the numbers, or at the same time. And this is an IC which uses a 4-bit carry look ahead adder. And the propagation delay of C1, C2, and C3 are equal, meaning it doesn't need to wait for the answer of C1 to come out to be able to calculate S2 and C2 and then S3 and C3. It could do all of that at the same time using this IC. And the inputs for this is going to be A0, B0, I1, B1, A2, B2, and A3, B3, and C0. And it could calculate S0, S1, S2, S3, and also C1, C2, C3, and C4 at the same time. But again, it's going to be a more complex system. Now, the same way that we created a binary adder, we can also create a binary subtractor. And we learned to subtract two binary numbers. We use the radix and the radix, the diminished radix, or in other words, we can use the complements to be able to calculate the subtract of two numbers or build a subtractor. Now, do you remember how we calculated the 2's complement of a binary number? What we did was we would change all the zeros to ones and ones to zeros, and we would add 1 to it, okay? So again, if we want to subtract two binary numbers like x minus y, we can write it like this: x plus negative y. And negative y is the first complement, and this is the first complement when we invert it, plus 1. So this part is going to give us the second complement. Now, to build this using logic gates, we can simply do it like this. Obviously, we need the binary adder, but the second number, y, we would invert all the bits. So it's going to go through 4 NOT gates, and we would add 1 to it. How do we add 1 to it? Ci or C0 would be 1. So we have added the 1 to it from here. Okay. Is it clear? So if we don't, one way to determine if this is a subtractor or adder, look at the C0. If it's 0, this is an adder. If it's giving 1, it's going to act like a subtractor. Now, we can also build a binary adder subtractor. And for this, instead of having the 4 NOT gates, we can have 4 XOR gates. And the other input of the XOR gate, one input is connected to Y's, the second number, and the other input is connected to a control signal or the mode signal M. And that mode signal is also connected to the carry or Ci or C0. Now, if this is 0, let's just check this. If Y0 is, let's say Y, the number Y is 1, 0, 1, 1. Okay. So Y0 is 1, Y1 is 1, Y2 is 0, and Y3 is 1. Okay. Now, what happens if M is 0? First of all, C0 would be 0. Okay. So we don't add anything to it. What happens if I XOR 1 with 0 for the first one? 1. Yes. What happens if I X0 again 1 with 0 for the second digit? 1. What if happens if I XOR 0 with 0? What happens if I XOR 1 with 0? So you can see that we have created a buffer using these XORs. Now, what if I give M equal to 1? First of all, C0 would be equal to 1. So that's going to add this 1 to it. Now, 1, 1, 0, 1. 1 XOR with 1 gives us 0. 1 XOR with 1 gives us 0. 1 XOR with 0 gives us 1. And 1 XOR with 1 gives us 0. So you can see that the output is the inverse of the input. So we have created a NOT gate. Okay. So simply by adding an XOR gate, instead of the NOT gates, we can create a adder subtractor. If M is 0, then F would be X plus Y. If M is 1, then F would be equal to X minus Y. And in one of your labs, you're going to build an adder subtractor. You're going to give it 2 random numbers like 2 plus 3. You have to convert that obviously first to binary. And there's another combinational logic gates that converts decimal to binary. And I'll show you how that works as well. You feed it through these 2 binary, a binary adder, and you can add them or subtract them. And this is actually the basics of any calculator that you have. Works exactly on this principle. You can easily use them as an adder, subtractor, multiplier. Again, multiplier is basically some adders combined together. Now, we also have unsigned binary numbers, and we have the 2's complement numbers. So the unsigned binary numbers, for those, we just can use a normal adder. So we're going to, for this example, it's a 4-bit by 4-bit. So we would have 4 full adders. And at the end, we want to have the carry. And for the 2's complement numbers, if we combine that with an XOR, we can create an overflow. And that overflow actually shows us if we have a negative number in the output or if we have a positive number, for example, in the output. And I will give you some examples later on for this as well. Another type of combinational logic circuit is the magnitude comparator. So this combinational logic circuit compares two numbers. We can have two 4-bit or 8-bit or 3-bit or 2-bit, but usually the ICs come in like two 4-bit digits. And it's going to have three outputs, equal, greater, and less. So A could be smaller than B, A is equal to B, or A is greater than B. And for example, here, if this number is 1101 and B is equal to 0111, then A is greater than B. So this would be 1 and the rest of it would be 0. Okay. So this is expandable to more numbers of bits. So you can have 8, 16, and so on. Now here, we're going to have 4, obviously. If we want to use a adder to determine this, x0 would be a0 bar b0 bar plus a0 b0. x1 would be a1 bar b1 bar plus a1 b1, and so on. And if a is equal to b, then we have x0, x1, x2, x3. If a is greater than b, then the equation would look like this. And if a is less than b, the equation would look as follows. So a prime 3, b3 plus x3, a prime 2, b2 plus x3, x2, a prime 1, b1 plus x3, x2, x1, a prime 0, b0. And the magnitude comparator, the internal circuitry looks like this. You can see multiple NOT gates in the input, and you have the bypass for the working as a buffer to the AND gates. You're going to have 8 ANDs in the input and 8 NOT gates in the input. We're going to have 4 XORs connected to the AND gates, and then after that, you're going to have 7 other AND gates, and finally 2 OR gates. And the equation that we showed previously, the function, you can easily, if you check it, it's going to create this digital logic circuit. Now, the way that we combine these, again, we can scale it up, is we can put multiple of these ICs in series. We can cascade them. And the way that we do it, we connect the outputs of the first one to the input I's of the second one, which here determines if A is greater than B, A is equal to B, or A is less than B. Do you have any questions from this part? No? Okay. So these are just for you to know. Usually I haven't seen questions from these in the FE exams, the competitor or the even the adder, subtractor. You would obviously see it in the lab, but there's not a lot of questions on it, FE exams about this. Another important, very important combinational logic circuit that we have is called the decoders and the encoders. So the decoders, they extract information from the code. A binary decoder, for example, we have a 2-bit binary number, and we would have 4 outputs. So a decoder has n inputs. It's very important. And 2 in the power of n outputs. A binary decoder is a very useful tool to convert a binary number, for example, to decimal and be able to show it. This is a very nice demonstration that you can see. So in this example, because we have two inputs, if I want to draw the truth table, I'm going to have 4 different outcomes. So 0, 0, 0, 1, 1, 0, and 1, 1. And I'm going to have 4 outputs. I'm going to call them D3, D2, D1, and D0. So if X and Y are both 0, then D0 would be turned on and the rest of them would be turned off. If X is 0 and Y is 1, then D1 and it's equal to 1. So D1 would be 1 and the rest would be 0. If X is 1 and Y is 0, then D3 would be 0, D2 would be 1, and D1 would be 0, and D0 would be 1. And if X, Y both are 1, it's equal to 3. So D3 would be on, and the rest would be turned on, off. Okay. And sometimes it's opposite. The D0 is 0, for example, the rest is 1. Okay, but one of them is going to be different. And for this example, you can connect that to 4 LEDs and to be able to show the output. And again, for example, let me give you another example. If we have 3 inputs, X0, X1, and X2, N is equal to 3. How many outputs would we have? 8. Thank you. So 2 to the power of N is equal to 2 to the power of 3 is 8. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Now, if X0, X1, X2 is equal to 1, 1, 0, then all of them are 0, D0, D1, D2, D3, D4, D5, but D6 is 1 and D7 is 0. So this is D6 because this is equal to 6. Okay. So D6 is 1, the rest of it it's 0. Is it clear, or do you want me to? Let's solve it for this particular example that you have here. What happens if X0, X1 is equal to 1, 0? Which of these LEDs would turn on? Number 0, 1, or 2? Yes, 1, 0 is equal to 2 if you can convert it to. So this would be turned on, the rest would be turned off. What if X1, X0 is equal to, sorry, my pen doesn't work on that side, is equal to 1, 1. Then this is equal to what? 3. So D3 would be turned on and the rest would be turned off. Okay. So this is a very nice animation as well. So for example, if X1 and X0 are 0, 0, then this is equal to 0. Therefore, D0 is equal to 1. And the rest of it is equal to 0. And this is a truth table for it. And it's the same thing that I draw as well. So if X and Y, and here you can replace it with I0 and I1, which are the inputs, input 0 and input 1. If both of them are 0, then output 0 or Y0 is going to be equal to 1. And the reason sometimes we show it with D, because it usually turns on a diode, or an output you can show it with YD, but I usually show it with D, because usually you can connect it to 4 different diodes and see which diode turns on. And like the same diode that you saw in the previous, or light that you saw in the previous slide. And if it's 0, 1, it gives us 0, 0, 1, 0. If it's 1, 0, then it gives us 0, 1, 0, 0, which y2 is 1 and the rest is 0. And if it's 1, 1, y3 would turn on, the rest would be turned off. So in a question, if you have a question in FE exam, and the question is, a decoder has how many inputs and how many outputs? The the answers are 2 in the power of n and n and 2 in the power of n and 2n and 2n and n. So always the decoder has n inputs and 2 in the power of n outputs. The encoder is the complete opposite, and I'll explain more about that as well. Now, if we want to build the decoder, it's actually pretty straightforward and easy. We usually used to do this in the lab. You need 2 NOT gates and 4 AND gates, and they are connected in this way. The AND gates are 2 input AND gates, and you're going to have, again, 2 inputs and 2 in the power of 2 or 4 outputs for this. Now, if we want to build a higher order decoder, for example, if we have 3 inputs, then we would have 2 in the power of 3 or 8 outputs. And we call it the 3 to 8 line decoder, or sometimes we show it like this, a 3 by 8. In some books that you would see that it's a 3 by 8 decoder. And for a 3 by 8 decoder, the circuit will look like this. You're going to have, again, 3 inputs, 8 outputs, but the AND gates are 3 input AND gates, and you're going to have 8 of them, and you're going to have 3 NOTs as well. Okay. Now, let's solve a quick example for this first one. Imagine if I2 is 0, I1 is 1, and let's make it like this. A2 is 1, I1 is 0, and I2 is 1, I1 is 0, and I0 is also 1. So 1, 0, 1. I want you to determine which output is turned on, and I want you to also solve it on the circuit as well. So the inputs are 1, 0, 1. Which output is 1 and perfect. So 1, 0, 1 is equal to, if we convert it to decimal, is equal to 5. So Y5 would be turned on. This one is 1, and the rest is 0. Now let's check it on the circuit as well. So 1, 0, 1. Okay. Because we have 1 at I2, the output of the NOT gate would be 0. So all of these are zeros. And in an AND gate, if only one of the inputs is 0, the output would be what? 0. So this one is 0, 0, 0, and 0. So all of these would be 0 because one of the inputs are 0. And the same thing for I0 as well. This is 1. So this would be 0, 0, 0, 0, and 0. Yes. Now, this one is connected to 0, so this one will also be 0. By the way, this was 0, 0, 0, and 0. And also this one, Y4, is also 0, so it's going to be 0. Now, we'll left with Y5 and Y7. Okay. Now, you can see that Y7 is connected to this line over here, which is 1. It is connected to the second one coming down here, which is what? 0. So the middle one is 0, and the last one is again 1 because it's connected to down here. Because one of the inputs is 0, this would be also 0, and this would be Y7 would be 0. What about Y5? Y5, one of the inputs is connected to I2, which is 1. The other input is connected to the NOT of I1. Because this is 0, the NOT would be 1. So the second input would be 1. And the third input is directly connected to 1. So 1. 1, 1, 1 gives us what? So Y5 is 1, and the rest of it is 0. Now, we can also add an extra pin to a decoder. It's called the enable, and we can do that for almost all the ICs that I've seen, combinational and sequential. They usually have an enable gate. And the enable gate turns on and off the logic circuit. In this particular case, if enable is 0, then the whole system would be turned off. No matter what the input is, we don't care. That's the reason we put X in it. We don't care what the input is. All the outputs would be 0. And when the enable is 1, it's like switching on or turning on our IC. And when adding an enable gate or enable pin, the only change that we have is we change the 2-input AND gates to a 3-input AND gate. And if in this scenario E is 0, one of the inputs would be 0, and we don't care about the other inputs. The output would be, regardless of that, would be 0. So it's like a safety switch to turn on and off. So if in the lab you connect a decoder and you change the inputs, you don't see any changes in the output, it's because it has an enable port, and you have to connect that to a positive 5 volt, for example, to activate the circuit, okay, to activate that IC. Now, we showed a 3x8 or 3 to 8 decoder. This is the truth table for the 3 to 8 decoder. And I think it's enough. Yeah, we can expand and build it, combine two 2x4s and create a 3x8. I think it's enough for today at this point. Let me finish this slide and then we can stop before the encoders. So to build a 3x8 decoder, you can combine two 2x4 decoders. And the only catch to this is that the decoders must have an enable, because the enable port or the enable pin allows us to be able to turn on one of them and turn off the other one to be able to combine these two. If it doesn't have the enable pin, we cannot combine them together and expand the decoders. And you can see that the third pin, I2, is connected to the enable of the first IC, and with a NOT gate, it's connected to the enable of the second one. Meaning when I2 is 0, this one is completely turned off, so everything is 0 here. And the second one is turned on. Okay. Now, I1 and I0 determine which one in this is turned on. So for example, if it's 1, 0, then Y2 would be turned on, and everything else would be 0. Okay. Now, if I2 is equal to 1, then the second one would be 0 and turned off. And if, again, I have 1, 0 here, then Y2, or in other words, Y6 of the system would be 1, and the rest would be 0. So this is 1, and the rest is 0. So you can easily expand a 2x4 or 2 to 4 to a 3 to 8. Now, some decoders, as I mentioned, are called the active high, meaning when you activate them, the output would turn to 1, the rest would be 0. In other decoders, it's active low, meaning that output would be 0 and the rest would be 1. And the only difference between active high and active low is in an active high, we use AND gates, and in active low, we use NAND gates. This is the only difference. So you can see here we have NAND gates. Now, a quick question. If in a decoder we have 5 inputs, how many outputs would we have?
30.
Yes. So it's going to be 5 to 32 decoder. Now I think we can stop at this point and we can continue with the implementation of the decoders using KMAP and midterms next week. Okay. I want to also speak about your next exam. I want to put the day for the first week of November. When are you comfortable to take the exam? A couple of students approached me and said they can't make they are not available on the first week of November. So second week of November, who wants to take the exam on first week of November? What about second week? Are you okay with the second week? Okay, so probably the exam for now is going to be on the second week of November on Thursday. The Tuesday before that, we're going to have a review session, and it's going to have everything that we're going to learn up to the end of multiplexer. Okay, so we're going to finish the multiplexer as well, and all of that is going to be part. So it's going to be chapter 1, 2, and 3. And I'll post another announcement for the online students as well. And it's going to be the same format as the first exam that you had. Okay. Thank you so much, and I will see you next week. And